Our next speaker needs little introduction. Daniel will talk to us about GR satellites.
Well,
Based on the line, it's very exciting.
thank you very much. I'm glad to be here for the first time, actually. So, what is GR satellites? GR satellites is a GNU radio out of 3 module, and it has a collection of telemetry decoders for many different amateur satellites. And by amateur satellite, I understand any kind of satellite which transmits data, digital data, on amateur radio spectrum. So these are satellites built by research institutions, educational projects and universities, also amateur individuals or small groups, things like that. If we see this as a small black box, the input to the decoder is usually IQ RF samples, either taken in real time from SDR hardware or a conventional radio like a Kenwood or Icom amateur radio, or maybe an IQ recording done with that hardware before. And the output you get from the decoder is either packets printed out in hexadecimal format, or you can save the packets to a file on your computer, or parse telemetry values. So those are things like voltages of batteries and buses, and current intensities, temperatures, and maybe even payload data. So some satellites have experiments, I don't know, maybe a high energy particle detector, for example. The main project goal is to provide an open source solution to decode any amateur satellite. So there's some philosophy to that any amateur radio signal needs to have clear public specifications for anyone to be able to build their own decoder, but that would be a matter for a different talk. This all started for fun and learning in 2015. Some small projects I did with a few satellites. No one besides the Orions had decoded before. And it sort of grew up and turned into a collection, which is mainly a 1 month project, but I'm always eager to collaborate with other people. So versioning, before summer this year, this was only working for GNU Radio 3.7, and it had just a master branch releasing versions 1.1, 1.2, etc. And since October, I switched it to GNU Radio 3.8, and most of the packet decoding is done in Python, so that was large but good change from Python 2 to Python 3. And now I have the main 3.8 branch, and I'm releasing versions 2.1, 2.2, it's 2.2 now on the branch. And I've kind of dropped development on the GNU Radio 3.7 version. So that is stuck in the past with the satellites that were supported before October. If anyone really wants a satellite which has appeared only for 3.8, I might go and backported it to 3.7. But this talk is about a large refactor I'm kind of doing right now to all the code base of GR satellites. This is in the next branch, and when it's ready, it will be released as version 3.0.0. So let's talk about how GR satellite looks like inside to motivate the need for this refactor. So each different satellite has its own flow graph. We're talking more than 80 different satellites, so that's a huge amount of flow graphs. Basic information is written in the README about each of the satellites or flow graphs, such as the kind of protocols for error correction, CRC codes it uses. So the README file is quite useful, but very, very long. And the flow graph contains all the things you need to turn IQ data into useful data. So you have blocks to demodulate the data, to run fault error correction, to pass the telemetry into useful values. Also image decoder for satellites which transmit JPEG data into small chunks. There's no GUI. The flow graphs have some configuration parameters, so the idea is you should run this as a .py script generated from GRC, from the terminal, so you can just say dash dash whatever parameter. And the input they get is standardized to getting UDP input, so samples streamed in real time using the UDP protocol. And these are real, not IQ. This was chosen because it's the protocol used by GQRX to stream data out, so you can interface your satellites easily with GQRX. Also, if you have a WAV recording taken from a conventional radio or something like that, or just from SatNox, it's not so much different from this. So interfacing to very different formats is always difficult. You need to handle different sample rates and so on. And from the point of view of output, you get everything printed out to the terminal or passed on to other applications via sockets or files. So an example flow graph we can see here. Here I have my pointer. We have the UDP input. And then some of you may recognize here an AFSK demodulator, so audio frequency GMSK actually. This is running with a GOMSpace U482C radio. So here we would perform the packet boundary detection to turn different packets into PDUs. Then FEC decoding. And here we end up with the useful packets transmitted by the satellite. So then it depends on your intended application for that. We can submit the packets to SatNox database with this telemetry forwarded block. And we also have a telemetry parser to print out human readable values. But you could do something like store into a file or whatever. So problems with this kind of approach. There's lots of repetition. As you can imagine, there's an FSK demodulator in many of the different flow graphs. So this is really difficult to maintain. If I want to change a single parameter for FSK demodulation or the kind of algorithm I use, I would have to go into maybe 50 different flow graphs, updating the very same thing in all of them. So that was natural and fine when there were very few flow graphs on satellites, but it has grown a lot, so this doesn't make sense any longer. At the same time, it's very flexible and not very flexible. So the user can go and change anything he wants. Let's say, as in my example before, you want to write the packets into a file or process them with your custom whatever, or send them out to an application using ZMQ. You can do that, but doing that is cumbersome. And if you want to do that for all the flow graphs, it's more or less impossible. And also for adding support to new satellites, which is something I do quite often as they keep launching more and more stuff, it's also cumbersome. So you copy as a flow graph for a sort of similar satellite and then modify the things you need to change. So the main idea for the refactor would be to eliminate all this redundancy. And the motivation is, well, let's see if we can come up with a way to describe what the things the satellite is transmitting, like have a simple text file with this satellite is doing this protocol with this error correction and these sorts of things. And then we should have code to read that text description and automatically figure out how to put together the decoder flow graph. And I identify 3 different use cases for this kind of refactor decoder. One is a standalone decoder, like a command line tool, where you say, hey, this is an IQ recording for this satellite, just decode the data for me and maybe print it on the screen or put it to a file or whatever. And so the command line tool should have enough command line options to be flexible. It should support different kind of inputs and outputs. Also, an important use case is as building blocks for other custom GNU radio decoders. Maybe people building their own ground station solution for the satellite. That's something that ESA did recently for the OPSAT satellite. So I recognize that there are users who want to go more advanced customization than just using the command line tool with everything built in. And also some other cool thing which I haven't gone at yet is a plugin. So this is reuse parts of GR Satellite, but not as I used to build something else, but from the point of view of an application. So I'm especially interested in hooking this to SatNox network from the server-side decoding point of view. So ground stations everywhere in the world submit the data to SatNox, and currently the decoding is done by the distributed ground stations. So this has the problem that whenever a new satellite is launched, if it uses really different protocols, they need to push the updated software to all the ground stations, and this is costful and it takes time. So SatNox people are also interested in, hey, can we do server-side decoding? So I think GR Satellite would integrate really well with that. But also a plugin for GQRX or any other SDR GUI app would be really great to have, like a pop-up menu. This signal I'm tuned to is this satellite, do something with the data. So key elements, there are two key elements for the refactor. One is what I call sat YAML files, and these are YAML files describing the satellite, basic information on the satellite name, NORAD ID, so on, and the protocols and transmitters. Why YAML? It's just because since GNU Radio 3.8 is doing YAML for GRC, flow graphs, and blocks, I figured out it wouldn't be such a bad choice to keep doing YAML also for satellites. So this is one part. The other one is components. The idea of components is to break up the decoding chain into logical, higher level functions. We'll see that in a moment. So the idea is you have your very simple blocks, you put them together into high level components, and then the way to write a SAT-YAML file is to specify what components you need to put together to decode the satellite. So that's what the standalone decoder do. It reads the SAT-YAML file for the satellite in question, figures out what components it needs to connect together, and runs a flow graph. But it's also possible for the user to go on GNU Radio Companion and use either high-level components or lower-level blocks from GR satellites to create any kind of custom flow graph. So components, speaking from the IQ data onto the final packet, you can break the chain logically into these four main tasks. The first one is demodulators. These convert the RF samples into symbols. Then decoders look at the symbol stream, detect the boundaries of the packets, perform photo correction, CRC checking, etc. So roughly this would correspond to the physical layer of the system. When we get to the upper layers, if we think of this as a network stack, it's kind of messy because you have CCSDS standard protocols, but many small satellites do ad hoc protocols. So you don't really have like a good separation between different network layers. So this kind of upper layer thing is handled by what I call transports. So whenever you want to convert from your physical frames into something else, maybe you want to perform defragmentation or things like that, or look at extra headers that would be implemented in a transport. And finally, data sinks are the blocks which do something useful with the data, be it to print it on screen with telemetry values, to submit it to some online server, to store it as a file, to parse a JPEG file, whatever. So if we look at the example before and we identify the functionality, all the part in red would be the demodulator, in this case for AFSK. Then these two blocks would implement a deframer for this particular GOM space radio. And then we have a few data sinks which do the useful stuff. So if we replace all the low-level blocks in the example before with components, we end up with something much more simple that it's easier to understand for many users and easier to reuse. So we have this AFSK demodulator, just turn any FSK signal into soft symbols. This GOM space U82C deframer, whenever I have this custom protocol transmitted by this GOM space radio, just detect packets, run for error correction, and spit out the frames as PDUs, and then the useful things we want to do with the data. So any user who wants to work with this kind of GOM space radio, he doesn't really need to know about fault error correction or anything like that. He just needs to know, well, it's this radio and it's transmit AFSK, so just put together these two blocks and you're done. So let's look at SAT-YAML. The example here is actually the SAT-YAML file for the satellite I'm using as example in this talk. The idea is to describe the protocols that the satellite is using in a component-centric way. And what I found is that many of the protocols are very ad hoc. So it doesn't make a lot of sense to try to chase like all these specific parameters. Of course, we could describe this kind of GOM space ad hoc framing by things like it uses Reed-Solomon CCSDS code and this kind of scrambler, and the header looks like this with some Golai error correction, but it tends to become really messy. So whenever I see something which looks kind of ad hoc, I just call it by name rather than trying to parameterize it. So in here, the framing we specify is just U48C. And that's the approach. So if we look at here, we have basic information like the main name of the satellite, alternative names, and you can call the decoder by using any of these names. The NORAD ID, this is used to transmit the telemetry to SatNox database. Also, you can call up the decoder using NORAD ID. So this is helpful to automate things. Then for the data that the satellite transmits, here we say we have a telemetry parser for the data, and the name of the telemetry parser, this is actually a Python class, is AU03, and here we describe the transmitter with parameters related to AFSK, and for the framing we just say it's the custom GOM space radio thing. So this is the list of modulations and framing supported. Modulations is something very basic, FSK, BPSK, and variations of that. But in the framings you can see some really standard things like AX.25 and some CCSDS protocols, but also some specific names of the satellites because they're using ad hoc protocols. You can also use SAT-YAML in GNU Radio Companion. So the way to do that is you have this satellite decoder block, and the satellite decoder block does most of the work that the command line tool does. So it gets IQ samples on one end, and on the other end, it spits out frames. So you're free to do whatever you want with the frames, but you don't need to know anything about the satellite. You just write the name or put here the path of a SAT-YAML file, and this block figures out how to put together the decoder. The standalone command line decoder looks like this. So you need to run it like GR satellites and then the name of the satellite, because the amount and type of command line parameters you get depends on what sort of functionality is needed to decode the satellite. So for example, for this particular satellite, we have fault error correction decoding, so there's a verbose fault error correction option, but there's no CRC, so there's no verbose CRC option. So the way this works is when you run GR satellites AU03, it looks at the SAT-YAML file, it figures out what kind of component blocks it needs to put together to decode this particular satellite, and then it asks every of those component blocks what kind of command line options would you like to put into the whole command line set. Telemetry parsers, this is something which was more or less present in previous versions in the same manner, but I'm relying onto it so much for this refactor. So it's done using a Python library called construct, which allows you to define how your data structures look like the first field is 8 bits wide and it's called whatever, voltage. And from this definition, you get a parser and an encoder for free. So we use the parsers, not the encoders, but if anyone wants to build a satellite transmitter, he could use the encoders. So new telemetry definitions can be written by writing this constructor class. And then this telemetry definition can be specified in SAT-YAML files and can also be used with the telemetry parser block, which just takes your construct structure and parses according to that. And currently there are 20 different telemetry definitions. There are many satellites without a parser. The format the satellite uses, for many of them, it's publicly available. So just because lack of time, I'm not adding more, but if you want to help, that is something you can help with. And something that the refactor also brings is a new file/image receiver. So there are several satellites which transmit file or image data broken up in small chunks. And the way each of the satellites does it is quite a bit different. Some tag the sample, some tag the chunks which are with a chunk number, so you get things like chunk 0, chunk 1, chunk 2. Some don't, and assume that you are not going to miss any chunks, and if you miss one chunk, you're screwed. Some don't tag the chunks, but rather say this chunk starts at offset 1000 bytes within the file. So the idea of this file image receiver is to have a general Python class that can deal in a generic way with these ways of transmitting data by chunks. And to use a specific protocol, you should derive from that class and implement the specific things. But for most of the protocols, the main functionality is already inside the general Python class. So the things you need to specify when deriving the class are very, very little. And in a few situations, it's enough to build a construct structure where you just say this field of the chunk is the chunk number, this is the useful data, this is file name, for example. So currently there's support for all these satellites. And roadmap, most of the things that were functional in V2 are now also in the next branch. I've been releasing alpha versions to engage with the community because I don't want to break not a functionality but workflows for people who are used to modifying flow graphs themselves or whatever. So just to engage with them, see if I break anything of what they were using, how well it works for them, etc. And currently I'm testing the performance of the modulators, and when this is done, probably I'll release V3. But there are many possible improvements which are made easier by this refactor, so this will keep appearing in later versions. And final question, what about integration with SatNox network? I don't know if there are any people from SatNox in the room. We have a thread open in the forums since 2018. Not much progress has been done about integration with GR satellites and SatNox, both on their side or on my side. So hopefully with this new architecture, it's much easier to put things together and interface. So that's all for today. Thank you.
We have a question over there, and if you're going to leave, please start very quietly, shuffling out of the room.
Thanks, Daniel, for the talk. I've got a question regarding testing and avoiding regressions or refactor reviews that you're doing. Do you have like IQ captures of all the satellites that you support and expect outcome that you run your flow graphs again? Or how do you do testing?
Yeah, the question was about testing and not breaking things with the refactor. So that was actually one of my major concerns, and I don't really have much in terms of unit testing. I have I have small IQ samples for most of the satellites, but not expected output, because depending on GNU radio version or some variations, some of the packets can be barely missed or barely decoded. So what I look at is that when I run the recording through the decoder, it at least produces some packets and they look sensible. For example, if you have a CRC and the CRC is okay, you can be pretty much reasonable. Maybe you lost a bit of decoding performance, but at least you haven't broken anything serious.
Have you also considered working on different channels with different modulation schemes? For example, your ground space SVR, can it transmit 2 different channels and communicate to 2 different set of satellites at the same time, and can work on 2 modulation schemes? Can this be done?
Yeah, the question is whether can we support a couple different channels. I guess you can.
Not just channels, also
You can.
modulation.
Yeah, also 2 different modulation schemes. So I haven't thought about this yet. I guess you can run 2 copies of the decoder or transmitter, but if you want some interaction, it's not better.
Okay, we got it.
So yeah, thank you.
11:50.